right, let's get going. So first things first, we have Carolyn here, who was just telling me about this awesome job she's got lined up in doing robotics next year. She's a senior and is going to tell you all about the CSX night, which is the Computer Science Exchange night. And you should come and you should get to know Carolyn, and you should try to be as smart as her because she's awesome and really smart. So I will turn it over to you, and there you go.
Thanks. Yeah, that was some high praise. But I am here, and CSX is really fun. You may have heard about some other events we've had throughout the semester. We've been holding a lot of idea exchange nights where we've been getting together and working on projects. Tonight we're having one at Tamper at 7:30 p.m. Tamper's down on Boston Ave. It's a great little cafe. And we're really gearing it towards students in 11 and 15. And what it's going to be is a pitch competition. So you can work with a team either on an idea you've already had, so just a problem that you want to solve, work on quickly prototyping a product, and then pitching it to us. We're going to be raffling off some sweet technology swag like Facebook, Bluetooth speakers, no big deal. Got a lot of cool sponsors. So it'll be a great chance to either work with people that you know or get to know other people in the department. There'll be a lot of upperclassmen there to kind of answer questions. And there'll also be a large community from the Tufts Entrepreneurial Society. So if you want to make some connections there and see how they also try to prototype ideas, it'll be a really cool event. There's going to be free food, always free food.
What time is it?
7:30 p.m.
7:30. That actually overlaps a little bit with our review session, which is, or for the Boggle thing, which is fine because I'm going to videotape it. You can watch it on the video, hopefully. So, anyway, sorry, keep going.
No, that's it. So we just hope to see you guys all day.
All right, you should definitely go. Thank you, Carolyn.
Oh God.
All right. So yeah, definitely think about going to that computer science exchange thing tonight. If you want to talk to other students in computer science, that's the place to go. And they do a lot of stuff around campus that they always participate in the hackathons, and there's always good swag. So you might as well get some of that. All right. So here's what we're going to do today. We're going to start talking about more. Actually, we're going to spend a whole bit of time on this thing called Dijkstra's algorithm, which is a shortest path algorithm that we'll get into the details of that. Here's what I think we should do. We will do a little bit on Dijkstra. I'll introduce it, and then we'll stop for a sec. Actually, this is kind of the end of Monday's lecture technically. And then we'll go to what's technically today's lecture. I will talk a little bit more about Boggle and about this review session that's happening tonight, or I shouldn't even call it review session, the how to get up to speed on Boggle if you're having trouble with it session, which is going to happen at 8 p.m. in Halligan 102. And which isn't that big of a room. So if you are considering going, it might be a little crowded. Bring a laptop, and we'll try to find seats for everybody if you do arrive. But it's going to be mainly question and answers and how to get set up and so forth. And then we'll talk about, we'll actually do some Dijkstra's algorithm practice. So I'm going to show you the algorithm, and you're going to go, yeah, I get that. And then I'm going to give you a piece of paper, and you're going to go, I have no idea what I'm doing. Right? So we're going to walk through that, and you're going to practice it. And by the end of that, you should have enough practice on that. OK, any questions before we get going? Anything? All right. So remember on Monday, here's what we talked about. We talked about graphs. Graphs are the Wild West of data structures. There is no particular structure to graphs. It's just a bunch of vertices and a bunch of edges connecting each other, or connecting the vertices. And then everything else is like, that's all you get, right? One of the things we generally try to do is find shortest paths between vertices in a graph, because that has lots of different applications, right? Google Maps is going to do that. If you're trying to get from here to San Francisco by car, they're going to start routing you, hopefully, one of the shortest paths possible. For whatever definition of shortest is, whether it's time or distance or whatever other definition, fuel cost, I don't know, however you want to do it. If you're basically trying to get through a graph from one vertex to another, shortest path. Okay? We talked about how to do that for unweighted paths on Monday. Relatively straightforward. Pick a starting point. Go add 1 to its adjacent neighbors. Go to the adjacent neighbors. Add 1. Keep adding 1. Marking paths or vertices as known when you find out what their shortest path is right at the beginning. So this is going to be a little bit different. This is this thing called Dijkstra's algorithm. It's probably one of the most famous algorithms in computer science, for what it's worth. Remember how I said quicksort was like kind of the first real big algorithm we see? This is another one where it's like another like algorithmic way to get some job done. And this guy named Dijkstra came up with it. He was a huge, huge computer scientist. Started his work in like the 50s, 60s, 70s. Did a ton of things. Came up with the solution to this. He was the first one to solve this problem algorithmically. And he actually didn't do it the most efficiently. We'll see how he did it, and then we'll talk about how to do it a little more efficiently as well. But that's this guy. He also has the letters I, J, K like next to each other in his name, which is kind of cool. And we use those letters all the time for loops and things, so I think that's kind of neat. Dijkstra's algorithm to find the shortest paths to all nodes from a particular node is what's known as a greedy algorithm. Okay, a greedy algorithm does the following. It says, what are my options right now? What's the best option that I think I can take? Take that option. Okay? And I will show you an example of greedy algorithms, and then you'll kind of get in your head what they're actually trying to do. But again, it's about saying, here are my options. What's the best one for me right now? It's greedy. It says, I want to do the best one right now. Even if that isn't going to be, in the end, the best, that's the way the algorithm works. Greedy algorithms work sometimes, and we'll see when they work for Dijkstra's, and sometimes they don't work. Okay, let me give you an example. Anybody ever work retail? Yeah, if you've ever worked retail, you know about making change, right? And I always screw up the people like the cashiers because they'll say like, oh, that's 43 cents. And I'll go, oh, OK, here's a nickel and two pennies. And they'll be like, what are you talking about? They don't know how to give me back the change. Half the time I get half the change back that I gave them because probably I screwed up in my math. But if you've ever made change, OK, how do you actually do it, right? If you have to get 63 cents back, don't you start with quarters first and say, how many quarters can I? You grab the quarters first. For 63 cents, you'd grab 2 quarters, right? And then you'd say, OK, now I have 13 cents left, right? And you say, OK, now what do I grab next? A dime. And then you grab pennies. If you do that, that is called a greedy algorithm because you're being greedy about getting to that 63 cents first. OK, what do? You grab the biggest ones first. And it turns out that for coins, for American coins anyway, doing the greedy algorithm will always give you the fewest number of coins back. OK? If you do, yes, it's true. If you do the greedy algorithm, it'll always give you the fewest number of coins, which is kind of the point. So for instance, let's say you had 15 cents you needed to give back, right? Well, you can't give any quarters, right? But you can give a dime, and then you go right to a nickel, which is the next biggest. For the first biggest is a dime, because that's the biggest that you can fit into 15 cents. Then you go to a nickel, and that's 2 coins worth, right? There are other ways to make 15 cents change, right? You could have 3 nickels, or you could have a dime and 5 pennies, or something like that. But every time you're going to end up with more than 2 coins. Okay, the greedy algorithm works. If we changed things and said, let's add another coin, right? Maybe some president that never got enough, I don't know, Polk. He was a good president. Let's put him on a coin. Let's put him on a 12-cent coin. OK, I don't even know what you'd call a 12-cent coin. What do you think? A what? A dozen? A dozen? Yeah, that work. I think I called it a 12er, right? But let's say you were trying to make 15 cents change greedily with that coin added to the other coins. You still have a quarter, you still have a dime, nickel, pennies, but you also have these 12-cent coins. Well, to make 15 cents coins, you go straight for the biggest one that fits into 15 cents, which is a 12, right? And then what do you have to do? 3 pennies. How many coins do you have? 4 coins. Where you could have done it with you still could have done it with 2 coins, right? If you'd skipped the greedy algorithm part and said, I'm going to go straight to 2 coins, then you would have had to do a different algorithm. The greedy algorithm in this case fails. OK, but do you get the idea of greedy algorithms? They try to do the thing that's closest to the solution now, right? That's what the greedy algorithm will do. OK, so Dijkstra's algorithm is a greedy algorithm. Turns out it does work for all positive labeled costs. OK, it will always work, and it will give you the shortest distance from one node to all the other nodes. OK, that's what it does. It will give you the smallest distance among all the unknown or all the other nodes. Here's how it works. OK, what do? You select a start. Just like the other one, you have to start at 1. And that's going to have a distance of 0 to get to itself, because you're home already, right? That's where you're starting. And then here's the key. Among the unknown vertices, in other words, the ones we haven't looked at yet, among those, you choose the shortest path and deal with that one next. You say, look, I'm going to be greedy. If I know that it's shorter to go to this one, I'm going to go to that one and try to keep the algorithm going. So you always go to the shortest one next. OK? And then you handle that node, and then you continue to do that. And you keep deciding whether or not it's a good idea to use a weight based on having to go back to a different node that you've already visited. And if it's going to be shorter to go there, you'll change it. If it's not going to be shorter, you won't change it. OK, we will do examples like this later, like literally on paper, so you'll see how it works. Here's a way to do it. Now, first things first, we set up a table, much like the table we had the other day, OK, for the unweighted paths. We list all the vertices down here. OK, we list all the vertices. Then we say whether they're known or not. At the beginning, we don't know the answer for any of them. OK, we're about to know the one for the first one. Then you pick one to start with. You say that's a distance of 0. All the other ones have infinity distance because we have no idea how short they are. So we're going to make them as high as we can to begin with. We also keep one other column here. Right? We keep one other column, which is the previous vertex. The one that caused this to change, we write down. OK? We do that so that we can actually figure out what the shortest path is a little bit later. OK? You'll see how that works kind of at the end of this. OK? So we're going to do that, and we're going to keep marking these as we go. See how this works. OK? We have chosen vertex 1 for our start vertex. OK? Vertex 1 is only adjacent to 4 and 2. In other words, the arrows out of it only go to 4 and 2. So we know how far it is from our current vertex to 2 and 4, and it is 2 and 1 for the distances, 2 to vertex 2 and 1 to vertex 4. So far, so good? This part's not that hard. OK? Then you mark this one as being known. Now, here's the part where the algorithm kicks in. Of the unknown vertices, 2 through 7, which one is currently the shortest distance from vertex 1? 4. So guess which one you have to deal with next? 4. OK? So you say, I have to deal with 4, and I'm going to go look at 4's adjacent vertices. OK? So we had to select 4. We look at 4's adjacent vertices. Now, 4 happens to be adjacent to a ton of different things. 4 is adjacent to 3, 5, 6, and 7. OK? So you update those if they haven't been updated already, and they all haven't, it turns out. So what you do, I forgot to mention, by the way, we put down the previous one. Vertex 2 was the one before it was 1, and the one before 4 is also 1. Now, for 4, 4 is adjacent to 3, and it costs 2 more to get to 3. So if 4 starts at 1, and it takes 2 more to get to 3, we write down 3 for vertex 3. You see how that works? You just mark down the additional amount you have to go. And we mark down that we came from 4. We do the same thing with the other ones. So for 6, it's going to be 8 plus 1, which is going to give you 9, because you started at 1, and you add 8, 9, and you came from 4. And then 7 is going to add 4, so that's going to be a total of 5. And 5 is going to add 2, so 2 plus 1 is 3, and so there 5 is now 3. OK? Now, we're not done yet, but we have now completed 4, and we have some paths in there. They're not infinity anymore. In other words, we can get to everybody. OK, you ready? We have marked 4 as now being known. Of the unknown ones, which one is the least? 2, right? So you have to do 2 next. So we have to go to 2 next and do it. And we select 2. Same idea. 2 is an interesting case, because look at 2. It goes to 5 and 4. Well, 2 plus, to get to 5, it costs 10 extra. So it would cost 12 to get to 5. 5 is already at 3. Are we going to update that to 12? No, because it's already 3. You don't update the ones that are already less. OK? So don't worry about that one. And then 4 4 is already known, so we're not going to change that either. And it also wouldn't be changed anyway, because you'd say 2 plus 3 is 5, which is already bigger than 1, so you're not going to change that. So now that we've done 2, we didn't actually change anything. We don't need to change any of these. Okay? All right, now 2 is known. Of the other ones, which one do we pick next? Yeah, it's a trick question. Pick 3 or 5. And this is one where you get to choose. It does not matter. So pick either 3 or 5. Let's pick 3. If we pick 3, right, then 3. So you look at 3 and you say, OK, it goes to 1 and 6. Well, 1's already solved, so we're not going to worry about that. 6, OK, 3 starts at 3, right? And 6, I believe, was, let me see, I think I already changed it here. 6 was 9, right? So then 3 plus the extra 5 to get to 6 means that it's now going to be 8 to get to 6, to vertex 6. And so we update 6 to be 8 now. And guess what? We also have to say, hey, the last one we came to is now vertex 3, because that's where we came to last, or from last. So far, so good? OK. So then now we have to deal with 5, because of the remaining unknown ones, 5, 6, and 7, 5 is the least. We do the same thing for 5. OK? And for 5, let's go back here and just make sure. 5 starts at 3. 5 is adjacent to 7, and that's it. So 5 plus 5 is 3. 3 plus 6 would be 9. 7 is already at 5. We're not going to change anything. OK? Not going to change anything. And then we have to next deal with 7. 7 is adjacent to 6. So 7 is going to be 5 plus 1 gives us 6. Look, are we going to change this one? We absolutely are. It's going to go down to 6. And then we're going to change it to be from V7. All right, so that's what we do there. And then finally, we can deal with V6. Well, V6 is not adjacent to anybody. So V6 doesn't need to change anybody. We mark it true and known, and we are done. OK? So you see how that works? Kind of get the idea? You're going to practice it in a little bit. So don't stress if you don't quite get it. You'll practice it. Like I said, some of you are going, OK, no problem. Then you look at the page and go, I have no idea what I'm doing, which is fine. You'll figure it out. Question. What's the path from the shortest path from V1 to V7? How do I find that? Let's do 6. V1 to V6. V1 to V6. How do you think you do it? Start at V6 and say, came from 7. So here's what I'm going to write. I'll just do it this way. I'll say, start at V6. That's where I'm trying to go to. Where does it come from? V7. Where's V7 come from? V4. Where's V4 come from? V1. And that's where we started, right? There's your path. V1 to 4 to 7 to 6. And that's the shortest path. And what does it actually equal? 6, right? 6, because that's how long it took. And you can follow that. So see how this algorithm will actually figure this out, give you the results? By the way, finding the shortest path, if you have this table, just a simple recursive program, a little recursive function here. You basically, excuse me, you basically you say, look, if the path is not a vertex or is not equal to a vertex, that's the base case, by the way. You print the path of the previous one, and then that's it. Right? And then you go back, and then it recursively goes and prints. Right? It would start at 6 and print V7, then go to V7 and print V4, and V4 prints V1, and V1 there's no value, so it stops. OK? See how that works? Nice and easy to print out the backwards. It's backwards for what it's worth, but that's the way it goes. Okay? Actually, it's not backwards. Now I think about it. It shouldn't be backwards because we did this before the cout. So we'll do boom, 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 and then print out on the return. OK, questions on that? That's Dijkstra's algorithm in a nutshell. We are going to practice that in a few minutes. OK? All right. Next. This is what technically we're now into today's stuff. OK? All right. Today, first thing first, we're going to talk about Boggle a little bit more. As I said, there's a review session, and we'll go into that in a minute. We're going to do 2 Unix tips of the day. We're going to double up today on Unix tips of the day. I've been storing one for a while, and then I just said, oh, let's get them both out of later now. Then we're going to do our algorithm practice, and then we're going to talk about some more best efficiency on Dijkstra's algorithm, and then we're going to talk about what happens if you have negative edges, which changes things a bit. Okay? Boggle. Tonight, review session, Halligan 102, 8 p.m. Like I said, it might be a little crowded, so I hope it won't be too crowded. But if it is, bring your laptops and I'll get cozy. Here's what I possibly are going to do. I don't have a real defined thing. I kind of want it to be your chance to ask questions, because if you don't get stuff, right? We can talk about how to get everything set up Eclipse, set up the files. Basically, type that one setup thing. It's not that hard. I will talk about how to actually do the publishing. So I was playing around with this the other day, and we did this we kind of did it for the lab. You remember one of the labs we had to make before we went to the website and tested it? It's the same thing here. You have to type in the folder that you're in. If you're in homework 6 folder, you have to type /publish every time you do it. You make, then you publish, and then you can use the website. So I was doing this last night, making all these changes and going, why isn't anything working? Nothing's changing. And then I realized I'd forgotten to do publish. So you got to remember to do that. But we'll practice that. We will talk about some algorithm ideas, like what's the recursive strategy you might want to use, right? Some of you guys have already figured one out. You might not want to use recursion. That's fine too. But if you do, or if you want to look at some other algorithm, then we can talk about that. We'll talk about how to use this dictionary class. It's basically just an interface. It's not particularly hard, but we can dig into that a little bit. And then testing your code. This is what I was talking about with publish. You can test the code on the website itself or on the command line if you know how to actually pipe in data. So you can do it. We'll work on that for a little bit. We might talk about handling QU. That's definitely a special case. It's kind of the wacky case in Boggle, right? That weird letter that's 2 letters. All right. And then there's also a way to show the same board every time. I put a Piazza post about that. I actually forgot, or I went and tried it again today, and I missed something on there, so I'll have to update that. But if you want to show the same board every time on the website, you can set it up to do that. And then you can test again and again without having to worry about it being a different board. So if you find a good Q board that you want to use, you can keep it on that one. OK? Questions on Boggle at this point for the class, if you're not going to go to the thing. Anybody have any concerns? Yeah, John?
Regarding the word Boggle list, sort of that structure going down, do we need to write a copy structure?
For the bog list?
Yeah.
You mean the
bog word
there's
list.
the bog word list. For vectors have built-in copy constructors.
I got yelled at using equal sign by
It probably wasn't. You probably got yelled at for using equal sign for some other reason. Probably not directly because of that. Did it say something about constructors? No viable overload. You should be able to do it. Stop by and see me sometime. We'll check it out. Yeah, or come by tonight. Yeah, good question. Other questions on Boggle? Is it going all right? You guys who have looked at it already? You who haven't, get to work. Gonna run short on time. It's pretty intense, right? I mean, it's not the shortest assignment in the world. OK. All right. If there's no other questions, we will do a couple Unix tips a day. I basically went over this the other day a little bit. I mentioned regular expressions. When we did use that sed program, I said, hey, behind the scenes, this uses these things called regular expressions. And regular expressions, I didn't talk about them, but I wanted to give you a little bit of a little tutorial on what these things are. There are entire books written on regular expressions, right? There literally are books you can read that talk all about how to use regular expressions. You will talk about regular expressions in Comp 170, which is the theory of computation class. Okay, you will talk about these things, and you'll talk about how to use them. You may also talk about them in programming languages or compilers if you take compilers class. Here's what they are. It's basically a string matching algorithm or way to do string matching. OK? Pattern matching, string matching, pattern matching. The most basic regular expression is a single character. Right? You can say that in the string A matches A in whatever string you want to put in. So for instance, A matches A, so it matches in the string the apple, it matches the A in apple, the A in was, the A in eaten. Right? If you want to match multiple letters, there's ways of doing that. You can put things in brackets. Right? You can say bracket EA, and it will match the E there, and the A there, and the E there, and the A there, and all that. It's kind of nice. You can match ranges. You can say match everything that's A through M. And it will go whoop. All those letters in red are A through M. OK? Yeah?
Can you make it also match only EA in order? Like E and A right next to each other?
If you wanted to match E and A next to each other, you would leave out the brackets. And it would match EA.
Okay.
Yep, just the brackets say any one. It's like an or. If it's in brackets, it's an or. This or that, right? OK, so that's what you can do. Those are some basic ones. OK, it gets even more interesting when you start talking about wildcards. OK, if you talk about wildcards, then a period matches any character. So if you say match A period period, it will match A followed by any character followed by any other character. Okay? So A period period matches APP and matches AS space. I had a hard time making the space red. And then ATE is A anything anything. Okay? A star matches 0 or 1 repeats of the previous character. So whatever the previous character is, it matches repeats of that character. So P star, right, will match P repeated any number of times. So it matches the PP and the P, and it would match a PPP and a PPPP. It would match all those. A period star, I did this wrong. This should just be, oh, actually, no, this one would work fine. A period star says A followed by any character repeated any number of times. So any character repeated is any character again, any character again, any character again. It doesn't have to be the same character, but that will match A and then anything else after it. Okay? Turns out you can anchor characters. So does anybody use Vim in here? I know a couple people use Vim. Yeah, if you use Vim, if you're not in insert mode and you type the caret character, it will go to the first part of the line. It'll go to the beginning of the line. If you do the $, it'll go to the end of the line. It's the same thing in regular expressions, right? If you match the caret THE, it will match the beginning. I shouldn't have the rest of this should not be red. It should just be the THE at the beginning. But it only matches at the beginning. It doesn't match any others down the line. Apple here does not match anything because it says find apple at the beginning of the word. D period $, says match D followed by any character followed by the end. Right? So it would match this. D followed by any character to the end of the line. Okay? See how these things work? They kind of build on each other, and they become super duper powerful, as it turns out. If you want, you can, if you did want to match definitely a period, you could put a backslash and say don't use this as a special character. Right? So the poisoned backslash period would match that. Poisoned backslash period would not match anything here because there is no period after that. And then the apple was poisoned yesterday. Just the period does match because it's a wild card for this space. OK? So I just wanted to introduce you to those things and show that. You can test these online. There's a bunch of websites. One's called regexpal. And what you can do is you can type something, some regular expression. Like let's say I wanted to match THE, right? I could say the quick, I don't know, what's something with the in it? The quick man ate the silly apple. Whatever, right? It matches the right there. OK? If I wanted to match T any letter, I could just do T period, and it would match both of these. And it actually highlights these. Sorry, the screen's a little small. There we go. It matches both this T something and this T something. See how that works? If we wanted to match like just, let's see, just something at the end. Let's see, PP dot star would match all the way to there. If I did PP dot, let's see, that's not a good example because I did on P, but let's say we wanted to match E, any character, only at the end. That only matches this E any character right here. All the other E any characters don't get matched. Yeah?
What if there are multiple instances and they overlap? Like if you do in this lowercase t period star.
Overlapping, lowercase t period star. It would do.
Because it should hit t and 8 and then t
Oh yeah, it generally does the start to the first one, and if it matches to all the way to the end, it just uses that. Yeah, the overlapping, it does the biggest one possible, basically. Yeah. So anyway, you will see these a lot, whether you do any other programming languages. Lots of different languages use them. Sed does, grep does, this one to search through files. Perl uses it, JavaScript. Python has regular expressions. You'll see them very often. Okay? So I just wanted to introduce them to you in that case. All right, the last little Unix tip of the day, this is just a really quick one. When you do setup for Boggle, we create a little what's called a soft link. And the soft link puts the following folder directly into your Homework 6 folder. And it actually just calls it data. It says that data is in your folder now. And you can get the files, for instance, the wordlist.txt file, straight from data there. You can't change that file, but you have access to it directly. It makes it so that you don't have to have this huge file. Like the word list, the actual list of words is like 170,000 words or something. And so you don't want to keep that in your own folder. So this actually links it directly to your folder. Okay? So you can get to it immediately. All right? You can't modify it, but you can actually get to it. All right? It's a good way to do that. We also do that with your public HTML folder files, so that if we find there's a mistake on the website, I can change one file, and then all of you guys get the change automatically, because you've all linked directly to it. Okay? So it's kind of neat that way. It's an interesting. Unix has some interesting ways of dealing with this, which is cool. All right. You guys ready to do some more Dijkstra algorithm? Here's what I'm going to do. I have a bunch of Dijkstra algorithm handouts. You guys know how the best way to hand out stuff through a crowd? No, not pass them out. Hand one to everybody near you. Just start handing them to everybody near you. And if you've already got one, pass them along. If you've already gotten some, pass them along. That's all. And eventually, these will filter back. But you just make it as parallel as possible. None of this like, yep, just grab them, just keep passing. I'll keep passing some up here. I'll start from the back. There you go. Just pass them to everybody. OK. Who doesn't have one? See how fast that was? These guys don't have one. Are there any extras? OK. Somebody wrote over and grab Jack. Thanks. OK. That was pretty quick handing out. Now, here's what you're going to do. Actually, I need one too. That might have one. Is there an extra, Jack? Yes. Thank you. Anybody else? All right. The page that we're going to do is the vertex, the one that says perform Dijkstra from v1. So flip it over to whatever page that is. Perform Dijkstra from v1. OK? I will start you out on this if you want. But basically, what we're going to do, right, is you're basically going to start at vertex 1. And this is a pretty intense graph. Right? It's got a lot of vertices and a lot of edges. Right? They're all labeled. But we're going to start from 0 or start from 1. That's at a distance of 0. Okay? And then you've got all the infinities here. So here's how you would start it out. You would say, OK, I'm starting from vertex 1. What edges are adjacent to vertex 1? 6, 2, and 7. Right? So you're just going to update that. You're going to go to 6, and you're going to say 6 is now 10, because it's 10 away from the start. And 7 is 25. And 2 is 20. And then you're going to update the previous to be all v1, the ones that you just arrived from. So v1, v1, v1. You get that? And then you're going to, all the others are going to remain the same. Dijkstra's algorithm says now, and then you're going to mark v1 as known. Dijkstra's algorithm then says, OK, if we now mark v1 as known, the next one we look at is of the unknowns, what's the one with the least amount? OK? Here's a tip. Once you mark one as known, you can fill in all the way across. saying, because you know that it's already been done, right? And by the way, this is going to be v1, and you're going to do this, make the first changes here. I'll draw it on the board if you're a little confused. Okay? I'll draw it on the board if you're a little confused. Okay? V, what do we have? Known, previous, initial, and then v equals 1. This is the way it's going to start out. Okay, v1, v2, v3, v4, v5, v6, v7. Okay. All right, and then nobody's known. And the previous one, well, there is no previous to anybody yet. I'll just leave them blank for now. And then the initial one is 0, and everybody else is infinity. So everybody else is infinity. And now we know that this one's going to be 0, and vertex is 1. This one's 0, and we said that 2, 6, and 7, so sorry, 2 is 20, 6 is 10, and 7 is 25. And then we can mark this as being from v1, from v1, from v1. And I already said that you can, because you now know this one, now this one's going to be true, you can just mark it 0 all the way across. Okay, because you're never going to change that one. If it's known forever. Okay? Man, did you get one of these yet? Oh, you got one, OK. You can start by looking at the board. If you can't figure it out, we'll get you there. If you find mistakes on mine, let me know. Or if you have questions. And if you get done, you can look at V4, but we're not going to spend too much time on that. Question, Greta? Sure. So this column is what we're looking at? Yeah, OK. So let's see. So this is when we were working on vertex 2. OK, so 2 was the one that was the least at that point because 2 was 20 and nobody else of the unsolved ones was less than 20. So we're going to look at 2, right? OK, so 2 is adjacent to which ones? Just 7. Oh, 7 and 3. OK, so to get from 2 to 7, how much more do you go? So don't you go from 20 to 3 more is 23? And so therefore, 23 is now the shortest path to 7. Right? And then let's look at 3, right? 2 also goes to 3. How much does it take to go to 3? 15. So 20 plus 15 would give you 35. But is 35, it's not less than 30, so you don't change the 3. See how that works? OK, good. Alex?
Shouldn't V4 be 28?
Possibly.
Because it's 25 to 3, and it's 3 from 3 to 4.
Hang on, we're looking at 4. So
It changes at V equals 3.
changes at v equals 3. So sorry, for 3, we've got 25 plus what?
3.
Oh, did I do that wrong? Which one? Here?
Yeah.
25 plus 3 is 28.
V5, I think, is the same as here.
OK, hold on. 28, 28, 28 probably, because we're still going to do that one. OK, so that means that some of these other ones are going to change, right?
Only V5. It goes down to 32.
You're right, 32. OK, thank you. Yeah. Question, Alexandria?
So at V7, when you go down from 30 to 25 for V3.
OK, hold on. So if we look at 7, 7 is at 23, right?
Oh, no, for V3, like go up a bunch of
I know, but we got to deal with this, right? We're in this column, right? You were in this column or no?
Yeah.
So when we're dealing with V7, we start at 23, and we say, which one is a V7 adjacent to? 6 and 3. So let's look at 6 first. 6 is already solved. So that's not going to go up, right? From 23 is definitely already bigger than that. So what about 3? 23, right? 23, how long does it take, or how much cost is it from 7 to 3? 2. So 23 plus 2 means that 3 would be less than 30. 23 plus 22 is 25, so we change that one to 25, because now it's shorter. And we hopefully also say that we get to V3 from V7. Make sure to update that too. You see how that works? Yeah. OK, other questions? Tafari?
So the order in which you numbered the top
Yep.
row, is that?
That's based on, at each stage, which one in the previous one was the smallest of the unknown ones. That's how the algorithm works. You look at the unknown ones and you say, which one's smallest? That one's the one. So for this column, how did I find 6? I went down here and I said, OK, 1 is already done. The next fewest one here between of the other unsolved ones is 6, because it's 10. So I say I deal with 6 next. See how that works? OK? Yeah. All right, seeing this on paper is a little tricky. Cornelia, question?
Why don't they all become null?
They do. I just didn't get there yet. Forgot to. I didn't update those. Thank you. OK. If you do the other one, and don't worry about it now, but if you on your own, you should probably do it. If you do the other one, you'll find out that some remain at infinity because you can't get there from here. Right? Anybody from Maine? Did we talk about this the other day? Yeah, you can't get there from here. Something they say in Maine a lot. Tafari.
So why
Y is what?
V1, why are they infinity?
Why are they infinities here? Well, so they
The one, like, the one right
here.
there.
So first, we haven't been able to get to 3, 4, or 5 by going to V1. Like V1 does not get you to 3, 4, or 5. So it's still impossible to get there so far. Right? Because 1 only connects to 6, 7, and 2. So we can't get to 3, 4, or 5 yet. We will later, but we can't get there yet. Okay?
Then, I mean, it's from the 6 only connects to 1, 7. Oh, never mind.
Yeah, just check it out. Let me just say that this is one of those foot stomping things, right? You will see one of these on the final, right? So practice this stuff. All right, you can get other examples online. There's lots of examples online. You could make some up yourself and do it. Do the V4 on the backwards on your own too, and we'll have to practice that. Okay. Any other questions on that example before we go on? OK. So I don't actually have the solution up here. You can download the solution. The solution is on the website. It's in an Excel file. I think it might be in a PDF as well. But that's that. So Dijkstra's algorithm is going to work. If you have positive weights, Dijkstra's algorithm will work to find the shortest path, right? But how efficient is it? This is a question we have to kind of analyze, right? When we were looking at the vertices, and we wanted to check a vertex and then see which of the remaining were actually known, and then find the smallest one, how many did we have to go through? Or in other words, let me phrase it this way. For every vertex, you have to go through every other vertex. What kind of performance is that? Yeah, it's n squared, or in our case, the number of vertices squared, right? So this is a squared algorithm, not so efficient. This happens to be the algorithm that Dijkstra came up with when he published his first paper on it, right? Other people in the meantime, actually some really clever people, I think, came up with some different ones. But this one is a v squared or n squared algorithm. The pipe characters there kind of stand for the number of vertices. Those of you in Comp 61 should know that by now, right? Number of vertices squared is the algorithm, right? So not so good. We don't like those ones. That's not a very efficient way. Trust me that Google doesn't do that when they try to get you from city to city. They'd waste all their processing power trying to get you there, right? So they're not going to use this one. Which one are they going to use? Well, by the way, most graphs aren't so dense. You don't know how long it took me to figure out all the different paths for this 5 thing, right? There's like 25 different arrows there. And I hope I didn't miss any. But it takes forever to draw this little thing, right? Because there's a ton of different paths, right? This would be a really dense graph. If it's dense like this, you're not going to get much better than v squared. You kind of have to go through all of them and check all of them like that. But if it's not dense, and most graphs are not, most graphs do not have this much connectivity. It would be crazy if they did, right? They wouldn't have, that'd be like everybody in this room having everybody else in this room as friends, right? That'd be a little weird, right? I guess I guess you could do it. I guess if we had one class or something, that would work. But that would be like super dense, right? We don't normally have dense graphs, right? Instead, what we can do, right? Well, I guess the question is there a better way? Every time we are trying to find what of this list? The smallest value. Do we have any other data structures which are pretty good at finding the minimum? Trees are OK. Not the best, though. What did I hear? A heap. Isn't a heap the perfect data structure? Because every time the root is the minimum, and that's what we're trying to look for, the minimum. So a couple of clever people, right, decided, why don't we do this? Instead of using like these arrays and like having to go through all the different vertices, keep the vertices in a priority queue, because that's exactly what a priority queue is. right? The idea is that the highest priority, or the one with the shortest distance, in this case the highest priority, is the next one we want. Keep them in a queue, or a priority queue, or a heap. Otherwise, they're more or less, the heap models a priority queue. And do delete min, and that will give you the minimum, right? If the node is already known, forget about it, because we already know it, and just ignore it, and then do delete min again. If not, we actually update the distances and put those new vertices into the heap. Watch how clever this is. It's like super duper clever. Here's our heap. It's a pretty homely looking heap, right? One number. We're going to put the starting vertex into the heap. Okay? And then we're going to take it out of the heap, because that's the way the algorithm goes. Okay? You take it out of the heap and you look at its adjacent vertices. You say, it's out of the heap, it's now known. We're dealing with it. It's going to be known. Take it out of the heap and then look at its adjacent vertices, 2 and 4. Mark those distances. You can still have a table. Mark the distances, 2 and 1 for the distances, and then throw them back in the heap. Right? And in fact, the heap, the distance will now be the priority for the heap. Right? So when you do this, and when you insert 4, or insert 2 and then insert 4, well, when you do an insert into a heap, the minimum bubbles to the top. You guys all know how to do that now. So the minimum bubbles to the top, and what's the next one we're going to remove? 4, which is the one we want, right? It's the one with the minimum. It's the one that's unsolved. That's the minimum, right? So we take the 4 out, right? The 4 is adjacent to a ton of things. Remember, in this one it happens to be. It's adjacent to 6 and 3 and 5 and 7. So we're going to have to put 6 and 3 and 5 and 7 in there and update their distances if we need to update them. If we need to update them, they go in the queue, priority queue, or in the heap. Right? So we have to update all of them. So we throw 3 in there, we throw 5 in there, 7 and 6. Turns out that these two have the same number of distance, but it doesn't matter. However your heap deals with it, it will get one or the other, and you can choose either one. Doesn't matter. Right? So now we've got the 3 and the 5. So the next thing, we took out the 4. The next one we're going to take out is the 2, because it's the one that's unsolved, that's unknown, that's the least again. We take out the 2. We deal with its adjacent ones. Now this is where it gets a little bit interesting. Well, not quite yet. Not quite interesting yet. The 2 is adjacent to 4, but 4 is already known. So we're not going to throw 4 back in there. We're not going to update it. It's still going to be 3. We're not going to update it. Right? It's also adjacent to 5. 5 is also doesn't need to be updated, because it's already sorry, that was 5 before. It's already 3. 5 is. So we're not going to add 10 more to 2 and make it 12. We're not going to change that, so we don't put that in there. So as it turns out, taking the 2 out does not change anything. If you remember, that's what happened earlier as well. The next one that's going to come out happens to be the 3. The 3 is adjacent to the 6 and the 1. Okay? The 6 and the 1. The 1's already known. That's not going to be a big deal. The 6 was 9. This was a 9 in the previous one. Okay? So the 6 says, so now we have 5 plus 3 is 8. 8 goes here, and we throw 6 in here. But 6 is already in here with a different priority. Turns out it doesn't matter. Which one of these 6s is going to come out of this heap first? The 8's going to come out first. We're never going to deal with a 9, because the 8's going to pop it out first, and then it's going to become known. And then when we get to this one, we're going to go, it's already known, forget it. Right? So it actually works. It's so clever. Okay, so clever. OK, then we deal with the 5. Same thing. The 5 is adjacent to the 7. And so the 5, let's see, 5 was 3 plus 6 is more than 5. So we're not going to update that. So we don't bother putting 7 in there. OK, and then we take out the 7. And the 7 is adjacent to 6. And guess what? The 6 was 8. And now the 6 is going to be 5 plus 1 is 6. So that 6 gets put in again, because we just updated it. And now the 6 goes in as 6. And it bubbles straight to the top. So it turns out that this one's the one we pull out next. And 6 isn't adjacent to anybody. So we are done with that one. And then we pull out the other 6 and the other 6, and we already know they're known, so we ignore them. And then the heap's empty, and we're done. OK, do you see how that works? It's really clever. Like, this is a super duper clever way of dealing with Dijkstra's algorithm. OK? This is the end result here. Asymptotic complexity of this. Aha! We still have to go through all the edges, right? We're going to end up traversing all the edges at least, once, right? We have to look at all the edges. For all the edges, we do a delete min, right? And a delete min, we already know that delete min is logarithmic behavior. It's just a bubble up, and it's logarithmic. So for each element, we have to do a log v. So we end up getting an asymptotic complexity of the number of edges log the number of vertices. Right? Does that beat the number of vertices squared? Unless, usually it does. The only time it doesn't is when the number of vertices is, or the number of edges is so huge that it ends up being basically another, kind of like v squared as well. So the previous algorithm would have worked fine, but it doesn't do any worse anyway. Okay, so it's so much better than that, right? Compare it. This is maybe insertion sort. This is maybe quick sort, right? Like, that's the difference in run times for these things. Okay. Questions on that? I know that was a lot of stuff, but seeing Dijkstra's algorithm in more efficient fashion is pretty cool. Okay. There are lots of other search algorithms too, by the way. There's one called A star. There's other ones that you can look up that are other different patterns, shortest path algorithms. This one happens to be the most famous, and it's still pretty good. Okay. All right, what happens if we all of a sudden put in a negative edge? The beauty of Dijkstra's algorithm without negative edges was that you knew you could say, once I reach an edge, once I reach a vertex and say what its distance is, right, and then deal with it, I can make it known. Once I handle a vertex and make it known, it will always be that distance. That's why I could I could go all the way across and go roop for any one that was known. Unfortunately, with a negative in here, you can't do that, because you might go down a path and then hit a negative back to a vertex that you already saw, and you'll have to go negative. It all of a sudden turns into a negative one. So is there an easy solution to this? I want you to think about this for a second. Talk to your neighbor. Consider it for a minute. Is there an easy solution to fix this? Or deal with this, I should say. You can be creative on it too. Figured out, Winona? Have any ideas? How do you deal with that for negative 40? What if it wasn't negative? OK, all right, you could try something like that. All right, does anybody have any ideas? What you might be able to do? Is there any way we can deal with that negative 40? Yeah. Yeah, that's not a bad idea. Let's do this. Let's make them all positive. So if we had, 41 to this, wouldn't this one become 1? And then add 41 to this, and 41 to this, and 41 to this. Does that work? Could we now do Dijkstra's, and would it come up with the shortest path? And then what? And then subtract 41? Would that work?
You have to know how many paths you touched, though.
Why do you have to know how many paths you touched?
You'd be adding 41 to everything.
Oh, very good. If you do that, notice here, I'll do it on the next one. if you do that, okay, adding 41 to all these, right, like this, right? Yeah, this is a very good solution, right? Don't pay no attention to the naive part, but it's a very good no really, I mean it's a good solution, right? I mean it's a good thought. But the problem, as Josh said, is hey, wait a minute. So if you go from 43 or from 5 to 4 to 6, now you're adding 40 extra here and 40 extra here, right? Which is not the same as just adding 40 extra, which is what would happen in the original case, right? You'd just add, or not even 40, you just add the original, right? You have a problem where the paths with many edges become much more weighty than the ones with few edges. And it doesn't break Dijkstra's. This will still certainly work for Dijkstra's algorithm, but it won't give you the right answer, right? It won't quite give you the right, it'll end up weighting these other multi-length paths by too many multiples. But it's a very good idea, yeah.
What if you just look and if you find a path that has a negative, then even if it's going to something that's true, you look at that one too?
Even if it's going to something, so what you're saying is forget about the idea of known vertices.
Yeah, ignore known, but only in the case of it's negative. Because that's the only time that it's ever going to be negative.
I'm not sure that's the only time, because let's say you go back in here, just because this one's negative, yes, you have to say, if this one's known, that's fine. But the fact that you've gone negative here might affect all the other ones as well, right? There's a carry-on effect as well, right? So you gotta be a little careful there. So yeah.
Sorry, follow up then. Then you make it. Then if you find a negative path to a known, you mark that unknown and you add in the path, and then you start over from there.
Yeah. Well, so you're kind of getting there. You're kind of getting there in the sense that the idea of a known vertex now is kind of out the window, right? You can't actually have a known vertex until you've done the whole thing. So you can't do that. So very good ideas. What you can end up doing, right? We actually combined the unweighted with the weighted one. Okay, we combined the unweighted with the weighted one, but the problem is we have to drastically increase the cost. This is going to end up being n squared in the worst case, but there's nothing we can really do about that. Sometimes that happens, right? Here's what we can do. Forget about these known vertices. Say we don't even have this column anymore. Known is not, it's dead to us. Right? So what we can do, though, the greedy algorithm is now broken. And remember how I said at the beginning, greedy algorithms don't always work. This is the case where it doesn't work. One of the cases where it doesn't work. Right? So what you can do is you can do this. You can say, let's use a queue. Right? Place the start in the queue. And then this is going to look a little bit like the breadth first search we did the other day. That's the part that's the unweighted kind of algorithm. What you do is at each stage you dequeue a vertex, and then all vertices that are adjacent to that where you would change the cost. So if you have to change the cost based on the current vertex, right? You then you throw all of those into the queue because you're going to have to deal with them again, right? You don't know them. You just changed them. You got to I got to redo them all, right? And you update it and then place it on the queue if it isn't already. For any of those, you update, you put it on the queue if it's not already there. You don't have to repeat them in the queue this time. But then you keep going through the queue until it's empty. Okay, so the idea is if you find one and update it, you can't guarantee that it's known now. You have to put it back in the queue and do it again. And you just keep doing that until the queue is empty. Yeah?
Doesn't this not stop
That's a good question. Doesn't it stop because it's an infinite loop? This example is purposely made to not have a negative cost cycle, right? You can't get from 7 back to 7. There's no way to get back to 7 so that you could have a negative cost cycle. So this will stop. This will stop. If you have negative cost cycles, you kind of walked into it a little. If you have, whoops, I guess I can go through the example in a sec. But let me go through the example in a sec. If you have a negative cost cycle, you can say, look, if you stop after every vertex has been dequeued the number of vertices plus 1 times, you will terminate with a legitimate answer, right? It won't necessarily be the minimum because there is no defined minimum, but you will have one where you're going to have the shortest path. It won't be the shortest if you somehow kept adding negatives, but it would be the shortest. Now let's quickly go through this example of how we do this. Okay, we throw in v1, right? Is it in the queue? Yes. Okay, we dequeue it and check the weights for 2 and 4. All right, 2 and 4 are, and I'm going to go through this pretty quickly so you don't have to pay too much attention to it, but basically 2 and 4 you had to update. Okay, we had to update 2 and 4, so they go in the queue. DQ1, right? So you DQ 2, and 2 actually goes to 5 and 4, but we don't update 4, and we update 5. Let's see, and do we have to change that one? Yes, because we hadn't gotten there before. So we throw 5 in the queue, right? DQ 5, check 5's weights to the queue, and so on and so on. Okay? DQ 6 and 7, and you're going to just keep doing it like that. Finally, you DQ 7, and you've gotten, you have to put 4 back in again. Because it's a negative weight, you actually have to put, because 7 goes, you update 4, you put 4 back in, and then, what is 4 right now? 4 is 1 right now, and then goes to negative 22, right? Because of the addition of negative 40 to whatever 7 was, which was 18. Okay? Then you DQ 4, check the weight. DQ 6, we have to update. Remember, this has follow-on effects. So then 4 changes 6, and then 6 doesn't change anybody. Okay? And so this is the final minimum path, right? And by the way, 3 you can't get to. It's infinity still. Okay? Questions on that? I went through this really quick. You can go back to the notes and walk through it if you want. But it's an interesting example, I think, of how you do this. Yeah?
How does the function deal with 3? And if you can't get 3?
It never actually. You can look at 3, but you never actually it never actually gets to the point where you look at it. This is a modified one. You never have to actually deal with it.
Yeah.
You know, you never actually. There's none of this idea of what's the minimum one anymore. Like, yeah, it just never actually deals with it because there's no point in. You don't need to deal with it. Yeah. Okay. Running time here. Edges times the vertices. Not so good. Kind of a n squared type of algorithm. We're not going to like that too much. Not going to like that too much. Okay, we already talked about negative cost cycles. You can stop if you DQ these things that many times. Terrible running performance, but if you have to do it, you have to do it. Okay? Google Maps would probably be, Google would be upset if all of a sudden it was like, took negative time to get somewhere. It would change all their algorithms. Where do we find Dijkstra's algorithm in the real world? All over the place, right? Shipping. If you need to ship things from location A to location B, you're going to probably want to find the shortest path. Okay? UPS. Did I mention this the other day about UPS? Left turns. They don't do left turns, right? Because they try to avoid left turns because left turns are hard. So, you know, they calculate these things when they're doing their shortest path, right? Gas, time, carrier cost, left turns, right? Computer networks. Computer networks are totally a graph, right? Your network, your computers connect to another computer, connect to another computer, connect to another computer. Total graph, right? And if you're trying to do a video chat with somebody in Australia, you don't want to hop from here to Ireland to South Africa to New Zealand to Australia. You just don't want to do that. The signal would be take way too long to get there, right? Have you ever tried this with someone? If you're Skyping with someone, ever tried to count in step with them, or sing at the same time as somebody? It's impossible. There's a delay in there that you can't figure out the delay. It's impossible. You hear things at a delay from when they do, and it's impossible to count. Try it sometime. You'll be surprised at how hard it is. I would do this I tried this with a friend of mine once, and I said, okay, I'm going to start counting 1, and you start keeping up with me, and I'd say 1, 2, 3, and then she'd go 4 after I said 4, and then I go 5, and she'd say 5, and she was trying to go along with me, but that's how she heard it, but not how I heard it. So try it. It's kind of clever. Telephone networking, which are just big computers these days, best path. So there's tons of different places you'll see shortest path algorithms in real life. Okay, if you take a networking class, you'll definitely see it again. Okay. What other ones? Well, mapping for subways and things. Shortest paths in mazes. You can solve some mazes many different ways. If you want to find the shortest path, well, you do a shortest path algorithm. You turn it into a graph, and you go, boom, shortest path. Okay. We'll be practicing shortest path, or we'll be practicing traversal algorithms in the lab on Monday, not necessarily Dijkstra's. And here's a paper I found online. Dijkstra's algorithm online, an empirical case study from public railroad transport. People are still using Dijkstra's algorithm for real-world things. Okay. All right. Questions about graphs, about Dijkstra's algorithm, or et cetera, et cetera? OK, I'll see you guys either tonight or next week.